This video is going to run through a method that we can use to solve linear systems called matrices. I'm not going to do much of an introduction into the idea of matrices. We're just going to use them as a method to solve systems. So let's start by considering a system of two equations with two variables. We've solved some of these in the previous videos. We learned we could solve by graphing, substitution, or elimination. So let's take a look at the system x plus 3y equals 5, 2x minus y equals 3. We can rewrite this system as what's known as an augmented matrix. And a matrix is really simply just a grouping or an array of numbers. A matrix is something that has rows and columns. In this matrix, I have created a row to correspond to each equation. So the first row takes the coefficients of x and y, so 1 and 3, 1 and 3, and then the constant that it equals is also in that first row. The second row contains the coefficients of x and y for the second equation, so 2, negative 1, and then there's the constant 3. This is considered an augmented matrix. Simply means it's separated into pieces, and I've drawn this vertical bar, which really represents my equal sign, kind of separating my coefficient matrix with the constants. So this is my system written as a matrix. So again, row 1 corresponds to equation 1, row 2 corresponds to equation 2, column 1 is my x coefficients, column 2 is my y coefficients, column 3 is the constants. Now, we're going to use a technique called using row operations to put this matrix in what's known as row echelon form. So first of all, row operations are just things you can do to equations. I can take any equation or any row and I can multiply it by a non-zero number. So if I take an equation, I multiply it by 2, as long as I do that to everything, the equation still holds. I can also add multiples of rows together. So I can add any two rows together. And that really is referencing that elimination method. We learned that if we want to solve this by elimination, we can multiply an equation by any constant, as long as it isn't 0, add the equations together, and we get a new true equation. So really, we're using elimination. We're just writing it in this matrix form. So those are my row operations. And then row echelon form, basically, if you look at your coefficient matrix, it should be a square, and you draw a diagonal line from top left to bottom right, everything below that diagonal line should be a 0. So if I have 3 equations, 3 variables, if I draw that diagonal line, everything below it should be a 0. And that's what we refer to as row echelon form. So let's see how that works with this particular example. So here's my matrix. If I want to put this in row echelon form, I draw my diagonal line. That means this 2 that I've circled in yellow has to turn into a 0. So I'm going to turn that 2 into a 0. And I'm going to do that by adding multiples of the rows together. So in this case, if I want to turn that 2 into a 0, I'm going to take my first row, and I notice that my first row has a 1 above it. So if I multiply the first row by negative 2, and then I add these together, that will give me a 0. My thought process is really similar to that elimination method. I'm thinking about how can I eliminate this? It represents the x's. How can I eliminate the x's? I multiply the first one by a negative 2. So I'm going to take negative 2 times row 1. I'm going to add that to row 2. Okay, so negative 2 times row 1 is negative 2, negative 6, negative 10. So just jot that down. And then row 2 was 2, negative 1, 3. And if I add those together, negative 2 plus 2 is 0. Negative 6 plus negative 1 is negative 7. Negative 10 plus 3 is negative 7. And so what I have gotten, this result, is going to become my new row 2. So I'm keeping row 1 the same, 1, 3, 5. And then I'm going to take this 0, negative 7, and put that in for row 2. And so now this system is in row echelon form. I should make one tiny comment. I'm calling this row echelon form, although traditionally, if it really is in row echelon form, you take the numbers along the diagonal and you actually turn those into ones. So in this case, we would take that second row, we divide everything by negative 7, so we could turn that number into a 1. I'm actually not going to take the time to do that because it turns out as long as we get those zeros below the diagonal, we can solve our systems. So just to give you a heads up, technically we should make all these numbers on the diagonal ones. Again, I'm not going to do that because I can solve the system without doing that. All right, so now we are going to use what's called back substitution to solve. And all that means is we're going to start at the bottom of our matrix. So we start with the second row and we translate it back into an equation. The first number is 0, so there are no x's. Minus 7y equals minus 7. So minus 7y equals minus 7. This is something I can solve by just dividing by negative 7. And I get y equals 1. Then we work our way up the matrix. So now I take the top row, which is the equation x plus 3y equals 5. I'm going to substitute y equals 1 in for y. So x plus 3 times 1 equals 5. Or x plus 3 equals 5. I minus the 3. I get x equal 2. And there's my solution, x equal 2, y equals 1. Now, this seems like a lot of work for a system of two equations with two variables. Technically, we're using substitution, but we're writing it out a little bit differently. And so I think in this example, maybe this method seems like a lot of work just to get the solution. But where this method is going to make more sense is when we start solving bigger systems of equations. That's the great thing about this method is we can use it for any number of equations, linear equations, and any number of variables. So for example, here is a system with 3 equations and 3 unknowns. And so let's see how this system works using this matrix method. Just to let you know geometrically what's happening here is these 3 equations represent objects in 3-dimensional space now. And they represent planes. I'll show you a picture of a plane later on in this video, but a plane, it kind of looks like a piece of paper that just extends forever, and we're trying to figure out where do these 3 planes intersect. So geometrically, that's what we're doing here. But let's solve this by first putting this into a matrix. So first row is my first equation. So I take the coefficients 1, negative 1, 1, and then the constant negative 5. Second row is my second equation. So coefficients 2, 1, negative 3, constant is 6. And that third row corresponds to the third equation, 3, 2, 1, negative 1. I'm going to put that line in there. That represents my equal sign. So if I want to put this thing in row echelon form, that means the 3 numbers I've just circled have to turn into zeros. So again, if I draw a diagonal line, everything below that diagonal has to turn into a 0. And so I'm going to start with this 2. I want to turn that into a 0. And so one way that I could do that, I notice above it is a 1. So I could take row 1, multiply it by negative 2, add it to row 2, and that'll turn that into a 0. So I'm going to jot down what I'm doing over to the side. This is a really good habit to write down what you're doing, especially if you're doing work that's graded by an instructor, because then they can follow your work even if you make a mistake. They can tell what was going on in your head. It also helps me keep track of what I'm doing. So -2 row 1 plus row 2 is going to turn into my new row 2. That'll give me a 0 in that first spot in row 2. Okay, so row 1 times -2 should be -2, +2, -2, +10. And then I'm going to take row 2 and just copy that down. 2, 1, -3, 6. I add those numbers together. I get 0, 3, -5, and 16. And I'm going to take that result and put it into my matrix. So first and third rows stay the same. And the second row is now 0, 3, -5, 16. Okay, I'm now going to do the first element in row 3. I want to eliminate this 3. I see that 1 in the first row, so I'm going to take that 1, I'm going to multiply it by -3. So that means I'll take the first row times -3. I'll add that to the third row. That's going to be my new third row. So first row times -3 should be -3, +3, -3, +15. I just jotted down my third row, 3, 2, 1, -1. Add them together, I get 0, 5, -2, +14. I'm going to put that in my matrix, so first row stays the same. 1, -1, 1, -5. Second row is still 0, 3, -5, 16. And I just took my result, 0, 5, -2, 14. Put that in for the third row. So now I have zeros below that first element in row 1. And so I have one more entry to make a 0, and that's this 5 in row 3. So again, everything below that diagonal needs to be a 0. All right, so if I want to turn this 5 into a 0, but keep in mind I also don't want to get rid of the 0 in the first element. I'm going to have to use row 2, a multiple of row 2, to get rid of this 5. Again, if I were to add row 1 to row 3, I would get rid of that 0 that I just obtained in that first element. So what I'm going to do is I'm going to take row 2, I'm going to multiply it by 5, and then I'll take row 3 and multiply that by -3. And that should eliminate that 5 in that second spot in row 3. So 5 times row 2 plus -3 times row 3 gives me my new row 3. All right, so let's see. 5 times row 2 would be 15, -25, 80. -3 times row 3, and then I guess, yeah, there was the 0 there. I didn't say that, but I wrote it down. So -3 times row 3, we've got 0, -15, +6, -42. I add those together, 0, 0, -19, +38. And so there's my matrix. Again, there's my diagonal, zeros below the diagonal. So now we're ready to use back substitution to solve this system. So I'm going to start. Back substitution means you just start at the bottom and you work your way up. So that last row with the 0, 0, -19, 38 corresponds to the equation -19 equals 38. I can solve this by dividing by -19, and I get z equals -2. Then I work my way up. Now I take the middle row. That's the equation 3y minus 5z equals 16. But I know what z is. Z is -2, so I'll plug that in. 3y minus 5 times -2 equals 16. That's 3y plus 10 is 16, minus the 10, so 3y is 6. Divide by 3, y is 2. And then finally, that first row is the equation x minus y plus z equals -5. I'm going to take my solutions for z and y, plug those in. So I get x minus 2 plus negative 2 equals negative 5. That's x minus 4 equals minus 5. Add the 4. X is negative 1. And so my solution, I can actually write it as, we'll call this an ordered triple. You can put the x in first. X was negative 1. The y is 2. And the z is negative 2. And so this now represents a point in three-dimensional space, which is where these three different planes intersect. All right, let's do another example. 3 equations, 3 unknowns. I'm going to start by writing this as a matrix. So the first row corresponds to the first equation, 1, 1, 3, 3. Second row corresponds to the second equation, 2, negative 1, 1, 3. And then finally the third row is negative 1, 2, negative 1, 4. All right, so I want everything below that diagonal to be a 0. So I'll start with the first column, and I want to make this 2 in the second row a 0. So to do that, I'm going to take negative 2 times row 1 plus row 2, and that'll be my new row 2. So negative 2 times row 1 should be negative 2, negative 2, negative 6, negative 6. And I'll add that to row 2. Let's see, row 2 was 2, negative 1, 1, 3. I add it, I get 0, negative 3, negative 5, negative 3. All right, so I took that result, put it in for row 2, row 1, and row 3 stayed the same. Still working with that first column. Now I want to make the negative 1 go away. To make the negative 1 go away, I can actually just add row 1 and row 3. So I'm going to take row 1 plus row 3. That's going to be my new row 3. So row 1 was 1, 1, 3, 3. Row 3 is negative 1, 2, negative 1, 4. When I add those together, I get 0, 3, 2, 7. So I have zeros in the first column. Now I move over to the next column. One more number I need to make a 0, and that's this 3 in row 3. I want to use row 2 to eliminate that 3, again, because if I were to use row 1, I would get rid of that 0, which I need to keep. So I'll use row 2, and in fact, all I have to do is add row 2 and row 3. So I'm going to add row 2 and row 3, and that'll give me my new row 3. So row 2 was 0, negative 3, negative 5, negative 3. Row 3 is 0, 3, 2, 7. I add them together. I get 0, 0, negative 3, positive 4. All right, and now we are ready to use that back substitution method to solve. So we start at the bottom. That bottom row represents the equation negative 3z equals 4. Divide by negative 3, I get z equals negative 4/3. Work my way up. The second row represents the equation negative 3y minus 5z equals negative 3. I'm going to plug my negative 4/3 in for z. So now I've got negative 3y minus 5 times negative 4/3 equals negative 3. 5 over 1 times 4 over 3, and it's going to be positive because they're both negative. So 5 over 1 times 4 over 3 should be 20 over 3. And then, I'd rather not deal with an equation with fractions, so I'm just going to multiply everything by 3. That'll clear the fraction. That's my least common denominator. So let's see, that turns the equation into negative 9y. 3 times 20 over 3, I can cancel the 3's out. I'm just left with 20. 3 times negative 3 is negative 9. All right, solve for y, so I minus the 20. Negative 9y is negative 29. Divide by negative 9. Finally, I get y equals 29/9. All right, one more variable, one more equation. That first row is the equation x plus y plus 3z equals 3. I'm going to plug those numbers in. So I've got x plus 29 over 9 plus 3 times negative 4/3 equals 3. So x plus 29 over 9, and then 3 over 1 times negative 4 over 3. The 3's cancel. That should just be negative 4. So then let's see, if I add 4, I get x equals 7, and then minus the 29 ninths. So x is 7 minus 21 ninths. No, I think I said that wrong. 7, yeah, 3 plus 4 is 7, and then we have to minus the 29 ninths. I need a common denominator. 7 is 63 over 9, minus 29 over 9, that's 34 over 9. And there's my solution. Happens to look a little uglier this time because we got fractions. But that's okay. This is still a point in three-dimensional space. X is 34 over 9, y is 29 over 9, and z is negative 4/3. That would be the place where these three different planes intersect in space. All right, let's take a look at one more example. I want to show you some kind of special cases that can occur when you're solving these three-dimensional systems. So here's my next example. We've got the system x plus y plus 3z equals 0, 3x minus y plus 2z equals 1, and negative 2 minus 2y equals negative 2x minus 2y minus 6z equals 0. So I took those three equations and I wrote that as a matrix. So same method as we always do, coefficients, then the constant, the second row, coefficients, then the constant, third row, coefficients, then the constant. So I'm going to go in the same order. I actually always work in this order where I eliminate first entry in row 2, and then I just go down. First entry in row 3, and then second entry in row 3. That's the order I always work in. So I'm going to eliminate that 3 in row 2. To do that, I have to take negative 3 times row 1 plus row 2. That'll eliminate that number. So negative 3 times row 1 is negative 3, negative 9, 0. I'm going to add that to row 2, which was 3, negative 1, 2, 1. That gives me 0, minus 4, minus 7, and 1. So I put that in for row 2. And now I'm ready to eliminate first entry in row 3. It's a negative 2. So if I take row 1 times positive 2, and I add that to row 3, that'll eliminate that value. So row 1 times positive 2 is 2, 2, 3, no, I said that wrong, 2, 2, 6, there we go, 2, 2, 6, 0. Add that to row 3, and something kind of interesting happens. We end up getting 0, 0, 0, 0. And so our matrix, first row is 1, 1, 3, 0. Second row, 0, negative 4, negative 7, 1. And that last row is now all zeros. So what does that mean? That last row actually corresponds to the equation 0 equals 0. This is a true statement. 0 equals 0 is always true. No matter what x and y are equal to, 0 equals 0 is always true. And so that means this system has infinitely many solutions. I'll show you a picture of what I mean by that in a little bit. But we would also call this a dependent system. It's a system with infinitely many solutions. There are some ways you can express an infinite number of solutions using a parameter. I'm not going to show that in this video, but feel free to ask me if you're curious how we can write this. For our purposes, we're just going to write infinitely many solutions, or you can write dependent system. So this is a special case. If the last equation, or it could be any one of your equations, I guess, simplifies down to a true statement. It has no variables left, and that true statement will always be of the form 0 equals 0. Then you have a dependent system, which has an infinite number of solutions. Now, there's a second kind of special case that could happen what if I modify my system slightly? I'm just going to put a 5. So let me go back. So this last equation equaled 0. If I make a tiny change to it and have it equal 5, then if you go through all this work, and I'm not going to repeat it, I think this video is already long enough, but basically, if you go through all the work again, that last row is going to turn into 0, 0, 0, 5. That corresponds to the equation 0 equals 5. Now we have a false statement, and that tells me that this system has no solution. These 3 planes never intersect, and we would also refer to this as an inconsistent system. It's a system that has no solution. All right, so visually what's happening here, here's a quick picture. So the different colors are supposed to represent different planes or different equations. And so in the first several examples we saw, the 3 planes intersect at one single point. And that's kind of, I think of that as like the normal case. We found our one solution. So 3 planes could intersect at one single point. And that would be, I guess technically you could call that independent and consistent, but one solution. Now, in my previous example, when I got an infinite number of solutions, what that might look like is the 3 planes intersected and form a line. And that's my infinite number of solutions, is that line that those 3 planes are kind of crossing at. It's also possible that 2 of the planes kind of lie on top of each other and then intersects the 3rd plane and forms a line. But basically that's your dependent system. They cross in a way that they form a line. There's a couple different ways we can get no solution. So here's 3 different planes again. You can see that you could have parallel planes that never intersect, or it's possible that maybe 2 of the planes are parallel, and so then there's no place where all 3 intersect, or your system might just look like a certain way where only 2 pairs of planes intersect, so there is no common point. Those are 3 different situations where you would get no solution. All right, so that is it for this video. I know it was kind of a quick look at how matrices can be used to solve systems. We're not going to go into much more depth about matrices, but if you are curious, you can always chat with me outside of class. All right, as always, let me know if anything is unclear in this video.